Hello, hello, and welcome back to the final piece of this link list installment. Let's take a look here. So we've already talked about creating and manipulating linked lists. We've done a little bit of comparing usage for lists and arrays and thinking a little bit about when we would use which ones. We'll talk a little bit more about that right away. We're going to do recursively traversing linked lists right away. We've done some drawing from memory for memory and reference diagrams. And we're going to talk a little bit about explaining the running and storage differences, although we also discussed that when we did our drawings of them as well. So the first thing we're going to talk about is writing an ordered insert for a linked list. So we've done an add to front, we've done an add by index, and now we're going to talk about doing an add in order. So before we actually do any of that, I haven't set up any code at this point in time. So I'm going to go ahead and set up a main file, I guess, and I guess I can just name it as is, whatever, that's fine. And we also are going to need a linked list class for this video. So I'm going to go ahead and just add that as well. Public class linked list, .java. And here we can have our node top, as we know, and we can have our linked list array, or sorry, not array, constructor. We're going to set the top to null. I'm just going to put it all in one line because it's literally a one-liner in this scenario. And then we're also going to make that internal node class right here where I can have, I guess we'll stick with object data and node next data and a constructor. Oh, I haven't been calling it OBJ. I've been calling it data. I want to try and get consistent here. This dot next is equal to next. Okay, so now we just have like the basics of our node class here. We have a basic structure. Here's our top. We'll write a method like, just because it's bothering me that this is underlined, I'm just going to write a method like is empty. And all it's going to do is just check if the top is null. Return this dot top is equal to null. There. So now I'm like using top, and now this won't be underlined in yellow anymore. I actually don't have any scenarios right now where I'm going to be calling this from main, so I'll turn it into private. But now that's yellow. That's okay. Oh God, no, it's killing me. Okay. So we'll just leave it like that. That's fine. So, okay, so now we have our basic structure. So that's great. So we're going to do some ordered insert here. Now, thinking back to when we were doing this with arrays, if we wanted to do an ordered insert, like as part of our insertion sort, we had to keep moving references around. It was crazy. We had a lot of moving pieces that we had to worry about. Here, we don't have to do that at all, which is super awesome. However, you cannot do a binary search here. One of the reasons why we kept things in order was so that we could do a binary search later on. But binary search requires random access. You have to be able to actually access the middle of the list without iterating through elements 0 to n over 2. You can't do that in a linked list. In a linked list, you have to go element by element. So we don't have random access. We have to use a linear search if we want to do searches through a linked list. Now, there are some other data structures that do allow for quick searching that aren't a linked list and aren't a linear linked list, I should say, and aren't an array or an array list. So there actually are ways around this problem that we have right now, but we'll see all those solutions in 2140. We don't see them in this class at all. So in this class, if you need to do fast searching, a linked list isn't going to be that helpful. The only way to do things in a linked list is linearly. We have to iterate through element by element. We can do a few little minor modifications that we'll talk about in a bit about like having extra links to keep track of where the front is, where the back is, things like that, but it still has to be element by element. There's no random access. That being said, there could be other reasons why we'd want to keep things in order, and so being able to do an ordered insert is actually pretty straightforward for us right now. We're going to write some code right now, an ordered insert example. This is an incorrect name of the file here, but I suppose I can update that. I better do it right now or I'll forget. We're calling it, what are we calling it? This is going to be the name of the folder. Be helpful if I named things the way I intended. Right here. Okay, cool. So things that we're going to need in order to do an ordered insert is, well, probably a way to enter like some kind of ordered method. And if we remember, we actually probably could use our get node method from the previous video. Now I did start over. My code here is starting over. So, oh, this is unhappy now with me. I have to reopen the folder here because I changed the name of it. There we go. So I did want to start over for this example, so we will have to make a get node method again, but that's okay. We can totally do that. Let's make a get node method that we're grabbing a given index. We can do a quick check here to make sure that the index is not, if it's less than 0, or if our list is empty. So now we can actually use the isEmpty method, or no, that's actually good enough. I don't have a variable to keep track of the size, but I did that on purpose. So we'll just be able to say if the list is less than 0 or is empty, we can just throw that runtime exception again. We can say throws new index out of bounds exception, and we can just say, oops, index is not indexable, right? Same as before. For some reason that didn't work. Check your code. We have to throw a new exception. That's not going to work. Okay, cool. Now, if that's not the case, if our code works just fine, we can make a node cur, and it can start at the top. We can grab a variable position that starts at the front, and we can now check to say if the current is not null. I'm trying to think of the best way to do this. And position is less than index. Walk through our list. Cur is equal to cur.next. Position plus plus. Now, just like in the previous video, order here matters greatly, because if this, or actually rather, order here does not matter so much, but having both is important, because if we hit null before this comes true, this value was too big. Yeah. And if this comes true before we hit the end, that's what we want. That means we actually found the element we're looking for. So we don't want to return null, because that means we fell off the list, but we should be able to return any real element. That sounds real. If I tried to pass in -1, that'll throw an error here. Good. So that makes sense. We can return cur. We now have a get node method from before. Okay, so now let's write this ordered insert. Public node, nope, public void ordered, lowercase o, ordered insert, and we're going to have an object that we want to insert. Okay, cool. So it's an ordered insert. So if we remember from a couple of weeks ago, we talked about searching and sorting. Basically, we start at the front of our list. We compare elements until we find the correct spot to put the element. And then actually, I wonder if get index actually made any sense here. Curses. I don't actually think we need get index. Oh, that's so depressing. Oh well, here we are. Good refresher from the last set of videos. My apologies. So we don't actually need that. Anyway, we're going to compare elements until we find the correct spot to put the element, and then insert the element. That's it. So let's start at the top of our list. And then we need to start walking through our list. We need to compare elements until we find the right spot. Now, in order to compare elements, we have to make sure that this is not null. That's a very important check always. And here is where that where the order matters. That's why I said it before, but was confused. Whatever, it doesn't matter. Because in order to find the correct position, we actually have to do a cur.data.compare to, right? We actually have to compare these two elements together to see where we are in the ordering. Insert. Now, what's obnoxious about this is that because we're using capital O object, we probably want to do some more of that integer.value of business to make sure that we use the integer version of compare to. Integer.value of insert. There are other ways to do this that some people might consider doing. And so this works, but as we can see, this line is like kind of long and annoying. So instead, something that we could do is create a to insert node. It's going to be a new node, and all we pass in is this object value. And when we do that, we can see that there's only one parameter here, and this one has two. So we need another constructor that only takes in the object, sets the data to the object, and then just sets next to null. It's just a standalone object that isn't connected to anything. But that's okay, because if we do that, this now works. And then we can basically do a compare to, but call a nodes compare to and hide away all of that super long line. So we can just say ncur.compare to insert. Like this. We can do less than 0, less than or equal to 0, whatever it might be. Now we have to go write this compare to. So we want to make sure that we're comparing two nodes. Now the question is, how do we want to compare two nodes? Well, right here we can say public int compare to. This is going to take in the other node, and we're going to compare two nodes here. So the first thing that we're going to do is we're going to get the value of this integer. So int1, terrible variable name, int cur is going to be this dot data. But this alone isn't going to work. There is this type mismatch. We're not currently converting appropriately. So we need to say integer dot value of like this. Is that going to work? No. Can we just cast it then, I guess, to an integer? Like that. There we go. We can just cast it to an integer. We can say that the other int is going to be casted to an integer, this dot, oops, not this, other dot data. And now we can do a comparison of these two integers. Now there's a couple different ways to do it. We can like leave these as big I integers and then just say dot compare to other, and it will do it for us. Or something that we can also do is if we want to leave them as ints and just do it ourselves, it's simple enough. We just say cur minus other int, because if those are the same, it's going to return 0. If other int is bigger, it's going to return a negative number, and if other int is smaller, it's going to return a positive number. In order to find the right position here of where we want to do our insert, we're probably going to want to also keep a node previous, just like our old add methods had. While our current value does not equal null, and this returns a number smaller than 0, so a negative number. A negative number means this is still big. This is still bigger than cur, bigger than cur, bigger than cur. I don't actually know if we need previous. We'll hold on to it for a second, but I don't actually know if we need it. Cur is equal to cur.next. So the question is now, when does this stop? Well, it can stop in two different scenarios. The first scenario is, actually it can stop in 3 different scenarios. We could be inserting top. That doesn't spell inserting, but whatever. Inserting bottom, like last, or inserting in the middle, right? So there's actually a few different scenarios in which we can do this insert. So if we're inserting at the top, that means that this never ran. So if we had like 22 in there, this was 22, and we were bringing in 1, we would end up doing 22 minus 1. This would be a positive number. So cur would be not null. but this would be a positive number. A positive number is bigger than 0, so this would evaluate to false. It wouldn't even go in the while loop. Previous stays as null. So if previous is still null, this is why we needed a previous. Or you could say if cur is still equal to top, let's do that because I really am not sure if we need it. If that's the case, we're inserting at the top. So then we need to say to insert dot next is top, and top is equal to to insert, right? So whatever's currently at the top becomes to inserts next, and then top now needs to be looking at the new front of the list, which is our to insert variable. Now, the next situation that we're considering is if we're inserting it at the very end, which means we went through the whole list and every single time to insert was bigger than cur all the way through. So if we made it all the way to the end and cur is null, well, that's very different then. We are inserting at the end. Let me pick this up and put it here. And if we're going to insert at the end, all we have to do is say prev.next is equal to insert. Now, to inserts.next is already null, so we don't have to do anything there. Turns out we definitely did need the previous variable. Let's go ahead and make this prev equals null to make it useful in a few places. There we go. And then our last scenario here is going to be inserting into the middle. So as soon as this breaks out of this part of the loop, it means that cur, when this breaks out, I want to make sure I say it exactly right. When this breaks out, it's because to insert should go in front of cur. So all we want to do is say prev.next is going to be to insert, and to insert dot next is going to be cur. And what in the world? This is exactly the same as saying this when cur is null. So we actually can fully get rid of this, and we only have to consider the top case separately. How funky is that? I'm pretty excited about that. Okay, cross our fingers and hope it works, right? Okay, let's go to the main and let's try some ordered insertions. We don't have any way to print right now, so I guess we should probably add a toString in here to do the printing. Public string toString. We're going to go ahead and print it. We take a cur node that starts at top. We're going to have some kind of a result that I typically like to do like this. I'll even put a space there, and then I can say while cur does not equal null, we're going to put cur's data onto here. And then we're going to say move to the next node. And then at the very end, I always like to tack on the closing brackets, and we can return result. So now I have a way of actually like printing out my list, which will be helpful. So now let's make a new linked list, ordered. And let's start adding things to it. We can say ordered insert. Let's add a 6, and let's copy paste this a few times. And here we're going to add to the front. Here we're going to add to the end. And here we're going to end up adding to the middle. And then after each one of these, we need to do a print. Oh, I called it ordered here. Sorry. One there, one there, one there, and one there. Just so that we can see each one. And actually, I'm going to just take this one step further, and I'm going to add a message here that says adding whatever number we're adding. I just think it will help us keep this a little bit clearer in our heads. And I'm going to add just some extra spacing as well. I just really want this to be nice and easy to see when we're looking at the output. 11 and 7. Okay, let's do it. Let's run. Let me pull this up here. And we can see first we added 6. Perfect, right there. Next, we added -1. It added it to the front. Next, we added 11. It added it to the back. Next, we're adding 7. And it added it to the middle. All of them worked. Our ordered insert works beautifully. Okay, so we did it. That's fantastic. So I'll make sure that I upload this code. We can see a little bit more about how we managed to get this running. Okay, let's continue. So we've talked about this ordered insert and how to move through our code in order to do so. But now we need to look at how to do recursion with linked list. So that X is supposed to be like recursion crossed with linked list. How do we recursively print a linked list in order from top to bottom, right? We're going to have to find some way to print in order or in reverse. So we can do a print in reverse. So we have two different scenarios here that we're going to talk about. Our print in order method, trying to think what would be easiest. Let's make these methods like not part of our toString. Let's make it separate so that we can keep using the same code base that we were working with, but they're not like the toString. We're just going to make brand new methods for printing. So don't need this get node anymore. We'll get rid of that. I was so excited about it, but I'll actually leave the is empty. Because I might use it at some point. Actually, let's use that is empty right here. We'll just say string result should start off actually like this, and we'll say if is empty, result equals empty list. I don't know, it's just nicer. Else, result can be equal to this bracket system thing that I have there. Pull all of this forward, not this, and put this there. Okay, just like nice to do like a empty list style method, whatever. Okay, but that's really not what the focus is supposed to be right now. I'm getting distracted. Let's do a print in order, public void print in order. So effectively, what will happen is printing. Our front end is going to go ahead and call right here ordered dot print in order. Now, what I'm going to do is, I just don't like that I did this. This was so dumb. That I put this like print each spot. That was not my smartest moment. There we go. That's fine. I don't want to have like 100 things printing, that's all. So each of these will have like their adding method, like, oh, we added this in. And then we're going to do a print in order. And this is going to have a helper method because by default, we can look at it and say, okay, we don't need to know how it's being implemented. So let's start with print in order. Let's just run this. Printing. Good. So it doesn't actually do anything, but it does call this. So let's start our print in order with this while loop. I'm going to copy and paste a little, but I have to change a bunch of it. So here we're going to say node cur equals top. And then rather than like this, we'll just say print cur dot data. At the top, I'm going to say print without the new line, these brackets. And at the end, I'm going to say the same thing. So if I run this, I should just get what I got. Oh, this shouldn't be a print line. This shouldn't be a print line. This should be a print line. Did I do it? There we go. So I get exactly what I got before, only now I'm calling print in order. So now rather than using my toString method to print, I'm calling print in order. And instead of returning a string, it's just printing all the pieces together, putting it at the end. This is obviously not recursive, but that's okay because this is going to be a great starting point for our for ourselves. Okay, so let's talk about recursion. How do we actually print this recursively? Well, we have to consider what the base case is and what the recursive case is. And typically when we're going from an iterative solution to a recursive solution, this is a good indicator of our recursive case. If cur is not null, it's recursive. Okay. So let's make a private version of this. Print in order, recursive, right? This will be recursive. And we have to figure out what we're going to do with it. Now, in order for this to be recursive, we are going to have to pass in node cur, And the reason I know I want to pass in cur is because inside this loop right here, that's really the only thing that I need access to in order to make it work, right? That's part of the conditional, that's part of this, that's all I really need. So in order to print in order, I just need to ask myself, is it null? If cur is equal to null, what do I want to do? Really, technically, I need to do nothing if it's null. I just need to not do anything. So I can just say like this. Anybody who's watching, I'm going to change this because we don't leave empty if statements. I'll change it in a second. So instead, this is our base case. We don't do anything if it's null. We break out of our loop. We could say that we do this and put this there. But I don't really like that, so I'm going to not. And then the inside here does system.out.print, and then it does cur equals cur.next. That is our recursive call. So right here, cur.next. We just pass in the next one. So now this whole loop just became print in order, and I could pass in cur, but I could just pass in top like this. Top. This shouldn't be there. I didn't even realize that was there before. Wow, I'm like such a space cadet. I had no idea that was there, but it's fine now. We're not going to leave this as an empty case. I hate that. We're going to flip this to say if cur does not equal null. This is our recursive case. I'll put it up here. And then right here, I'll just say base case do nothing. So now when I run this code, my output did not change, but it totally works exactly the same, which is important because we're not actually trying to change the outcome. We're just trying to change the implementation. Okay, so awesome. We did that. That's super exciting. So now we're printing it in the order in which we expect to find our data because it's an ordered insert and we're outputting it in order ascending. Now I want to give us this option of printing in reverse recursively. Not printing it recursively is a real pain in the butt. In fact, I strongly recommend you take a few minutes. It will end up being like probably 30 minutes. So not really a few, but like take time and try and figure out how exactly would you print a linked list in reverse if you already have a formed linked list. Like just take a second to think about it. I'd like need to go to the last element, then the second last element, then the third last element, then the fourth last element, and the fifth last element. And I'd have to keep doing that until I was printing top. That is n squared. That is 2 for loops nested or while loops nested inside each other. The first time I go all the way to the end, the second time I go to the second from the end, because there's no random access. You have to start at the top and go all the way to the end. Now, there are special kinds of linked lists that could keep track of where the end is, that could have a connection to its next node and its previous node, but that's not what we're working with. So what we actually can do is quite clever. Let's go ahead and make another call here, ordered.print in reverse. So new method that we're going to make right over here, public void print in reverse. And it's going to do something very similar, except instead of calling print in order, it's going to call print in reverse. Print in reverse. Node cur. Now here's the kicker. This code is almost exactly the same. So I'm literally going to copy paste it for a second. The only difference, if I run it, you'll see it's the same. The only difference is that instead of printing first and then recursing, we want to recurse first and then print. This is mind-blowing. I hope it's not just me. Mind-blowing. That didn't do what I thought it was going to do. It is, oh, it's just because I'm not calling print in reverse each time. That's why. Whew, got it. There we go. I was like, why didn't that work? Okay, that is mind-blowing. All I had to do was switch the order of the calls. Boom, it works 100% of the time. Crazy. This is because of how the runtime stack actually works. So when we do it this way, when we did it originally, we like printed and then iterated to the next element, printed, iterated to the next element, printed, iterated to the next element. However, in this case, we use the runtime stack just like our own built-in stack of pancakes, where we keep making pancakes before anything prints out. make a pancake, make a pancake, make a pancake, make a pancake, make a pancake. You make all of your pancakes into this big giant stack of pancakes. And then once you have no more pancakes left, so once cur is null, then you can start to eat that pancake. So this runs. And the freshest pancake comes first, which in this case is 11. The last element. We eat that pancake, hop, 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 hop. We eat it. We move back to the next one. We go to the next level of our record. So to the second last pancake that got created. And that one was the 7. And so we end up printing in reverse. And all we had to do was switch the order of operations, recurse print versus print recurse. And we end up with 2 very, very different answers. So it's pretty, I think, crazy, mind-blowing, and also can be really tricky to follow. So hopefully this can help shed a little bit of light on what the heck is going on. So yeah, so order really matters. Sometimes we do need to draw this out so that we can see it. So the take-home message when it comes to linked lists is the following. We have now learned how to build our own data structure linked lists, and they do actually exist directly in Java. There is a built-in linked list Java class that you can look up, but this is how it works. We've created our own. It really only requires 2 very, very simple classes, and we've nested them inside each other, linked list and node. It's pretty straightforward. And the linked list class is where we put all of our stuff, right? Any adds, removes, toStrings, everything happens through the linked list class, not through the node class. All the node is a vessel that contains the information. We don't actually do very much with it other than hold our data. Everything happens in the linked list class. It's very important that we remember whenever we're implementing a method that we don't lose any links. So we have to make sure that everything is accounted for, nothing gets orphaned and taken away. We also want to make sure we think about those special cases. Having that connection to top can make things easier, but also really tricky. We can't forget that that is considered a special case, and we often have to handle it separately because we have to move that top pointer around accordingly. When in doubt, draw it out. And if you find yourself sitting in your desk chair at home and you're like drawing it out in the air, stop what you're doing and then draw it on paper. I can't tell you how many times people come to me and they're like drawing it out with their finger in the air. And I'm like, what are you doing? Just write it down on paper. It helps so much to visualize it. If you're looking for some sample problems, the same goes as before. Anytime you're iterating over a linked list, feel free to now use recursion instead. If you want to find a really awesome big program to build, consider building the game of war, like the card game of war, using linked lists, because it is super wacky and tricky to keep track of all those different links and pointers and connections. It's pretty wild. So it's a really, really good way to practice is to do the game of war, just to get a lot of good practice in. Like I couldn't recommend anything more than that. Okay, so that's all I have when it comes to linked lists. We're going to start talking about interfaces and abstract data types next, which is even more powerful. Lots of good things to come. Thanks, everyone.